Oh, okay, I think we're on now. This is Big Daddy K, and I'm here to show you a DC shunt motor. This is basically our drawing here of a DC shunt motor. I'm applying a DC voltage source here. So here's my positive, here's my negative. I'm injecting a positive to A1. It's going to go counterclockwise. That's a motor rotation. A2 is getting connected to negative, F2 gets connected to negative, and F1 is connected back to positive. This IL now for math becomes line. I line. This is still ET terminal voltage up here. EG would be in here, and this is where your little resistance of your armature is, just like before. But now what happens is current flows this way. It goes here, and it goes here, and it all comes back to this point. So now your armature current's different. It's basically I line subtract IF equals IA armature, no? Or you could say IF, IA subtract I line equals IF, right? Vice versa. So what I got for you here today, I got this thing here. This basically takes an RMS signal in, as you learned in AC theory, and gives me an average DC voltage output. This is going to be my rheostat for this position. All I'm really doing is varying the voltage. I'm not really playing with this here, but this could be in here. There's also one other control you should have in here, but I don't need it because I have a variable voltage. Let's just get rid of all this. Our current flows. This here, this has got to be set at high resistance on startup. This is called your armature rheostat, no? And you will always see this in motors. This limits the inrush current to that armature, otherwise it would just take off. This here is like, instead of this being a magnetic force, this becomes a counter EMF. So this shunt field basically produces a counter EMF against that armature. So it's basically blocking it. So when I go over here, I just got it connected up shunt, just our little motor here. A1's positive, A2's negative. I got F2 connected to A1, and F1 is connected positive. So I'm going to turn this on. I got about 100 volts there, you'll see. I changed the speed, I can overspeed it. I'm essentially pulling more current from my line. My voltage went up, so my currents are going up. But this is what happens. You notice how I'm telling you this counter EMF here? This counter EMF is what limits the current flow through this armature right now. So if I open this circuit up, I basically lose all this counter EMF. Therefore, there's no pressure against this armature, and it will just speed up and destroy itself. So I'm going to demonstrate that to you. Right here, I got to be quick on the draw. They do have field loss protection relays. They might install a relay in here with a contact in here so this doesn't happen. So if this ever loses power, this contact will open up. We'll just assume that it's energized right now, no? So it's closed. This loses power, that opens up and protects this armature circuit from overspeeding. So I'm going to show you what happens if that's not there. Whoa, see, it just totally took off on us, hey? So, whoo, yeah, so you got to be quick on the draw here. Just overspeeds, and it will just overspeed and overspeed and overspeed until it pretty much kills somebody or destroys itself, though. So let's check that again. Yeah, that's it. You'll notice everything goes haywire here, no? Well, watch that, eh? That's pretty cool. That's a high reluctance path starting to speed. Whoa. So if you ever lose your field, it's going to overspeed and take off and kill somebody, you know? So, whoa. I don't know how fast that RPM's getting, but I'm pretty sure it's getting about 10,000 RPM right quick. Yeah? So this is basically a shunt. So this is just a thing about the shunt, the DC shunt motor. Once again, it's the most useful. because you can have either above or below base speed controls. When we start looking at this more, this one here is going to be above base speed. This one here is going to be our below, no? I just look at it as here's the horizon, this is above, and this is below. That's how I look at it, no? But these above and below base speed controls mean a lot, because when you start looking at the graph, it could go like this. This is my horsepower, this is my torque. This is base speed right here. This is below, and this is above. So when I control that one rheostat, the armature rheostat, I can control my torque at 100% from here to base speed. Base speed is pretty much full load and the full RPM. So that is pretty much, you got 100% torque. Once you start basically giving up this goes to above base speed. So if this was 1,000 RPM, you could actually run this motor to 2,000 RPM, let's say, or to 0 RPM. If I fall this way, I'm going to get lots of torque. If I go over this way and I change this control here, the below, this is our armature rheostat. This one over here is our above, so this is our shunt field rheostat. Otherwise, just similarly summed up as the governor, because governor means a speed operated control. Well, this is kind of pretty much the graph that means everything to you. So over here, if I control my armature rheostat, I can lose horsepower, but I have 100% torque from no load to full load. If I go over here and I'm running at my base speed, I can touch my shunt field rheostat and give myself more speed, but my horsepower maxes out, no? Because you can't make a motor any more efficient than what it is. It just doesn't work that way. So it's pretty much what it comes down to between the torque and the horsepower and the RPMs, no? Just like in three-phase machines, if I get torque, I basically get speed here, but when I start losing torque, I get speed, just like in our three-phase motor section. So once again, I'll thank you for your time, and we'll do one more little whoop. Whoa. Yeah. So that's what it's supposed to do, so don't get worried. So if you hear that noise and you don't know where the shutoff is, hit the deck, right? Thanks for your time.